Alright guys, Medically here again. Welcome back to the YouTube channel. So today we have 3 questions to solve, and yeah, let's go into it. So question number 1 says determine the crystal structure for the following. A metal with lattice parameter of 0.4949 nanometer, atomic radius of 0.175 nanometer, and 1 atom per lattice point. Then B, a metal with lattice parameter 0.42906 nanometer, atomic radius of 0.1858 nanometer, and 1 atom per lattice point. Okay, so we are being given the lattice parameter for 2 different questions, A and B. So the first one, we are being told that the lattice parameter is 0.4949 nanometer, and sometimes it might be given in Armstrong. So if you are given in Armstrong, you divide by 10 to become nanometer. If you're given in nanometer, you don't need to go backwards. It's always best to solve in nanometer. So the other question says we are given 0.42906 nanometer, right? And we are both given their atomic radius. For the first one, the radius is equals to 0.175 nanometer, and the other one is radius of R, which is equal to 0.1858 nanometer. So this question, they want us to determine the crystal structure. Is it simple cubic, is it body center cubic, or is it face centered cubic, right? So now we need to look for the relationship between the atomic radius and lattice parameter. For each of these guys, we input our figure, then whichever one relates. So for simple cubic SC, relationship between A and R is equal to A is equal to 2R. Then for our BCC, the relationship between A and R is A is equal to 4R over root 3. Then for our FCC, our A is equals to 2R, sorry, let me use the small r since I've been using small r, root 2, right? So since we are given A and R, we substitute in each of these 3 equations. Then whichever one gives us our A to be the same thing, we say cool, we are good with it. So let's do for number 1. So for number 1, we are going to be applying our 2R for each of this equation this, and this. So let's begin to apply the equation. Let me change my ink. Let's use yellow. So for the first equation, our A is equal to 2 times 0.175, which is equal to 0.135 nanometer. So for this guy, it is wrong. So let's try that of BCC. Our A is equals to 4, open bracket, 0.175 over root 3, which is equal to 0.4041, right? That's nanometer, which is also wrong. Now let's try that of FCC. A is equals to 2 times our R, 0.175 times root 2, which is equal to 0.49497 nanometer. So this is our answer. So since this is our answer, right, we can go ahead and say that our structure is FCC for A. So let's go ahead and just write it here that this structure is FCC. So for our B, we are going to repeat the same process to figure it out. So again, we go, I think, let me just do it beside here, right? So we are applying the first one, which is A. Sorry, let me change my ink once again. So for B, or number 2, we say our A is equal to 2 times, what's our radius, 0.1858 nanometer, which is equal to 0.3716 nanometer. So this is wrong. It is not simple cubic. Let's try that of BCC. A is equal to our 4, open bracket, 0.1858 over root 3, which is equal to 0.42908 nanometer. So is it the same thing? Oh yeah, it's almost like it. that's because of this 6, but let's confirm, let's solve that of FCC before we decide if that is truly our answer. 0.1858 times root 2, sorry, let me erase this, root 2, which is equal to 0.5255 nanometer. So from this equation, this guy is wrong, then this guy is correct, even if our conversion is, hey, sorry. So from here we can determine that this guy is BCC structure. So question number 2 is BCC structure. Yeah, so we are done with question number 1, right? So let's go to question number 2. Figure 4.7 shows the result of an X-ray diffraction experiment in the form of the intensity of diffracted versus the 2 theta diffraction angle. If X-ray with a wavelength of 0.15418 nanometer are used, determine the crystal structure of the metal, the indices of the plane that produce each of the peak, and the lattice parameter of the metal. All right, so we are being given figure 4.7 right here, guys. Cool, that's clear enough. So let me use my yellow ink. Right, next. So given this image, we are being told to look for the peak values, right? The indices of the peak values. So indices of peak values are things like 111, our HKL, 110, 101, 211, 232. They said we should look for that. And we are being told to look for our lattice parameter, which is A. And remember, whenever you're solving, everything has to be in nanometer, right? And we are being told to look for what else? Lattice parameter and the crystal structure. So first of all, the way to solve this, if we're not given the table, is you come here into the image, right? When it comes to X-ray diffraction, all that matters to us is our 2 theta, which is the diffraction angle, right? It is all that matters to us in solving. So when you zoom into this image, usually what we do is we count. We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is now up to 9 dots. So what I'll do is I'll say 10 divided by 9, which is equal to 1.11. So I would be counting 1.11, 1.11, 1.11, summing them up until I get my figure. So for this peak value, right, I trace it down, which lands somewhere here. Cool. So what I do is I have 10 here. 10 plus 1.11, 1. Okay, instead of doing the sum, let's just count. So I have 0. This is my 0, right? But it's not 0, it's 10. But I'm just assuming this is my 0. I count 1, 2, 3, 4, 5, 6, 7, right? So that's 7. So what I'm going to do is I'll say 10. Sorry, let me erase that. I'm going to say 10 plus 7 times 1.11. So let's do that and see what it's going to give us. 10 plus open bracket 7 times 1.11, which is equal to, I had 17.77. So this will be my 2 theta for peak 1, right? So we call this peak 1, peak 2, peak 3, peak 4, peak 5, peak 6, peak 7, peak 8. So we have 8 peaks in this diagram, right? So let's try and look for that of peak 3. You can do peak 2 yourself. It's actually simple. It falls under 21 right here. So you won't call it 21. Remember, it's not 10 lines. We have 9. So we divided to know that each line is 1.11. So that's going to give us 21.11. So let's do that of peak 3. So we count again. This is our 20. Right, so we do 1, 2, 3, 4, 5, 6, 7, 8. It falls under number 8. So we say 20 plus 8 times 1.11. So which will give us our 2 theta is equal to, which will give us 28.88 degrees. Remember, diffraction angle is degree, right? So let's zoom out. So there's something else I want us to always understand. There are some questions they get to give you and they tell you find the diffraction angle. So when you solve originally, you have to make theta the subject from. Let's assume we get theta to be 10 degrees, right? Don't ever leave your question this way whenever you're solving x-ray diffractions, always multiply this theta by 2. So you have to do 2 theta, which is equal to 20 degree, because when it comes to x-ray diffraction, all that matters is 2 theta. Theta is useless in x-ray diffraction. We don't use theta. We always use 2 theta. So don't forget that. But in this question, we're not told to do that. We're being given our 2 theta. So questions where they give you other parameters and tell you to look for your theta or diffraction angle, you first of all find your theta, then you multiply by 2. If you leave your answer in theta, you're gonna fail it. But this is the correct answer. So let's move forward. What else? Okay, yeah, we found 2 of our peak values, right? So this is the table. We found our first, we found our second, and we found our what peak value did we find? I think it was the third. Yeah, it was the third. So let's see if we are correct with what we are being given in the question. So in the question we're told it was 18. So as you can see, I did mine. I got 17.77, which is approximately 18. Cool. We are on track. So the second one, I said it was 21.11, in which here we are given 21. If you approximate, it's 21. So I got that as well. So for the third one, I said mine was 28.88, but here we are given 28.5, which we are on the same track. Why do some questions give us this angle instead of allowing us find it ourselves the way we did it here? So the reason why they do that is because, for example, now whenever they are marking, right, whenever they are marking, it's going to be too stressful for them to like start tracing each and everybody. So imagine the first person chooses his own as 18.8, 18.11, the next person chooses is to be 17.77. So during marking, they have to like calculate your own, calculate this person's own, calculate that person's own, which will take a long time in marking. So that's why they save themselves the stress and just give you the number. So they expect everybody's figure to be the same. So imagine everybody's in 18, 18, 18. So there's just going to be one mark guard in which they will use in marking everybody's question. So let me just reverse my steps. Right, so now they've saved the stress by giving us the angle they want every of us to use, or each of us to use, while solving, so they can easily mark our question. So yeah, I'm trying to revert all of my steps, yeah, rather than erasing. So now let's go into our table. Right, so whenever you're solving for number 1 or number 2, that's when you see questions that has this this graph, the XRD graph, right? You get to draw a table. So in this table we need 7 to 8 columns, right? The first one is the peak index. Remember, we counted 8 peaks here. 1, 2, 3, 4, 5, 6, 7, 8. That's the peak. So that's why I have 1 to 8 on this first row, right? So on the second row, we are given our 2 theta. We get to find or input all of the figure of our 2 theta. So also you begin to find your theta. So our theta is 2 theta divided by 2. Remember, we made theta the subject formula. So if 2 theta is equal to 9 degrees, so what will be our theta? Theta is equal to 9 degree over 2, in which, sorry, not 9 degree, it was 18, but then this is an example, so let's just do this correctly. So 2 theta is 18 degree, so it becomes 18 over 2, which is equal to 9 degrees, right? So can you see that's how we got our 9 degrees? So you repeat that in every question or every row until you get that. So that's how we got to derive each and every one of our theta here. So far, sine square theta, we punch it to our calculator saying sine, open brackets, our theta, which is 9 degree raised to power 2. This is what you type into your calculator. So let's assume we never found our theta. This is another way to find this row. That's what I'm talking about. Another way to find this row is we put in our calculator sine, open bracket, 18 over 2 raised to power 2, right? You're still going to get the same answer, which is the 0.0245. We're still going to get the same answer. So usually some people be like, oh, I don't need to find my theta. It's best you find your theta among you create a column for your table, because if you're needing theta while you're solving somewhere in front, so you don't have to like start going back to like start punching calculator to look for that. So it's best you always look for your theta to be on a safe side, right? So yeah, that was how we found everything in this column. Yeah, so I'm going to revert my step now and erase this as well. So now coming to this column, right? What are we doing there? So what we are doing in this row is we begin to take each and every one of our thetas, right? We take each and every one of them, then begin to divide them by the smallest of them on this column. We begin to take each and every one of our sine square thetas, all of these guys, divide them all by the lowest on this column, right? Which is this guy. So we divide everybody on this column by that lowest guy, which is 0.025. Then we begin to get our numbers, right? Okay, so in the first row, right, we said 0.25 divided by 0.0245, 0.0245 divided by itself, which gives us 1. So that's why we have 1 right here, right? So let's do for this other guy, divided by 0.245, which will give us 1.355, right? Which is approximately 1.4. So for this next one, punching into my calculator, I got 2.473. Punching this in my calculator, 2.473, which is approximately 2.5. Sorry, this is 5, 2.5. Then the next one, I got 3.331, which is approximately 3.3, right? Then the next one, I got 3.857, which is approximately 3.9. Remember what we are doing, we are dividing each and every one of them by the lowest, which is 0.0245, right? So I'm going to erase that now. And here I got 5.078, which is approximately 5.1, sorry, 5.1, right? Then the next one I got 5.853, which is equal to 5.9. Then the last one I got 6.233, which is approximately, sorry, this is approximation. Let me erase this. Approximately 6.2, right? Cool. So guys, in this next step, right, we want to begin to multiply to expand. So whenever we are solving, let me do this. Whenever we are solving, right, for our next step, this rule, right, there is something very paramount that we need to always pay attention to. It never happened here, but I want to show it to you. I'm going to write it right here. I think I should write it right here. Okay, let me write inside this column, which is not supposed to be here, but I just want to write it so it can be on the same row. You get to understand. So let's assume we got 1, 2, 3, 4, 5, 6, 7, 8, right? Always pay attention to number 7, but most of the time we used to have 9 to 10 picks or 8, 9, 10 picks. So let's assume we have it down to 15 also. Always pay attention to always pay attention to 7 and 15. Why did I say that? So the reason why we pay attention to 7 and 15 is because when we are deriving these indices, right, we are trying to say 1 square plus 1 square plus 1 square, which will give us 3, right? So if we say 2 square plus 2 square plus 0 square, that will give us not minus 0 square is equals to 8. Sorry, is equal to 8, right? Let me write that well. That will give us 8. So if we say 2 square plus 1 square, right, plus 0 square, that will give us 5. So there is no way we can derive that of 7. That is why we are always going to avoid 7, right? And 15, the same thing goes for 15. There's no way we can derive 15. 16 is 4 square plus 0 square plus 0 square, which is equal to 16, right? And before 16 we can have 3 square, which is 9, plus 2 square, right? 9 plus 4 is 13, right? So there's no way we can derive 15. So that's why we are always going to avoid 7 and 15. But since most of the time the peak never gets as long as you get to see 15, right? So but just know those two numbers, 7 and 15, always avoid them. So now some people are like, okay, what happens when we get to see 7 in our equation or 15? What you do is you begin to multiply. For this one now, it's a whole number, right? Sorry, revert. For everything here is a whole number. Sorry, everything here right now is a whole number, so we are just going to multiply by 2. So in some cases, you don't multiply by 2, you multiply by 3, 4, 5, or whatever. I'm going to teach you how to know when to multiply by 2 and how to know when to multiply by 3. I'll show you that next. So if we multiply here by 2, we have 2, we have 2, 4, 6, 8, 10, 12, 14, and 16. So here now we can easily find all of those 2 raised to power 2 yada yada yada, 3 raised to power 3 yada yada for all of them, unlike when we're stuck that we could not find for 7, right? So I'm going to revert all of my steps now. Okay, so I said previously that I will teach us how to know when to multiply by 2 and by 3. So I already did that in a sheet of paper, and I took the picture to show us. Sorry, where's the picture? I placed the picture here. Okay, here's the picture. Oh, I placed it twice. Let me delete this. Delete. So here's the picture. Now let's go through this picture. Right, so in this picture I took the liberty of multiplying by different figures. So some people might be like, why did I multiply by 1.43? So I multiply by 1.43 because sometimes I don't like to approximate my decimal points, right? Because sometimes when you approximate 6.5 and when you approximate 6.8 or let's say 6.9, right, they might fall into close digits like 14. So whenever you're numbering things like this, whenever you're trying to get these figures, you don't want to see anything happen repetitively. Like you don't want to have, okay, see, for example, you don't want to have anything like repeating itself. Like where can I show that? Okay, I think I'll show that in another question. You don't want to have anything repeating itself. Like probably maybe we've been having series here, and here we get to have like 8, right? Okay, see, for this place now, I'm 100% sure I probably got repetitive figure, so that's why I stopped. So we don't want to have repetitive figure. That's why I generated this thing, which is 1.43. So some of you might be like, how did I get the 1.43? This was what I did. So for this question number 1, right, I wanted to derive 2 here from this decimal point. So what I would say is 2 divided by 1.4, which will give me the 1.42 yada yada. So I approximated to 1.43. So by the time I begin to apply and multiply by 1.43, I began to get all of this in this place, right? So I'm just going to erase that so you can see. So when I multiply by 1.43, it was going well. 1 times 1.43 was 1.4, so I approximated, I got 1. I got my 1 back. 1.4 times 1.4, I got, and I approximated, I got 2. I did the same thing here, approximated, I got 4. I did the same thing here, approximated, I got 5. I did the same thing here, approximated, I got 6. I did the same thing here, approximated, I got 7. So the moment I saw this 7 in my equation, I knew that no, 1.43 is not the guy I want to use, because originally I was supposed to have 7 here. So when I multiply by 1.43, I'm supposed to get rid of 7 and escape, with another digit, probably 15 or 13, right? So because I saw this 7 here, I told myself 1.43 is not the guy. So let me just multiply by 2 originally, right? So that's why I came here and I begin to try multiplying by 2. So it's always about try and error to make sure you avoid 7 and 15. So I started here. I begin to multiply 2 times 1. I got 2. 2 times 1.4. 1.4. It is approximately 1.2. Right? 2 times 2.5. I got 5. Yes. Then 2 times 3.3. I got 7. So the moment I saw 7 again, right? Can you see 7 is the guy that is always chasing me around? The moment I saw 7, I said, no, 2 is not my guy. So let's assume 7 was here, and I said 2 times 7 here, I'll be getting 14. I can go on, but because 7 was already appearing in my multiplication, right? So it's already appearing in my multiplication. And don't ever do that when you see 7 here, you begin to multiply by 2 again. No, rather just, since you multiply twice, which is 2 times 2, that's 2 times this, then 2 times this gave you 14. Just multiply by 4. You feel me? Don't do like multiplying twice. Just multiply once, but be sure the number you want to use to multiply. That's why I brought out a jotter to do that first in the raw book. So the moment I saw this 7 again, I knew that okay, 1.43 is not my guy, 2 is not my guy. So let's multiply by 3. So I began to multiply by 3. 3 times 1, I got 3. 3 times 1.4, approximately this. 3 times this, I got this. 3 times this, I got this. So the moment I saw that I skipped 7 in this row, sorry, let me erase. The moment I figured that I escaped 7 in this row, right? I knew that, okay, 3 is correctly my guy, right? But while I was multiplying by 3, I'm coming. While I was multiplying by 3 in this place, I got 15. So you can see that it is shaded, right? I got 15. So the moment I got 15, remember I said the two number we need to always shy off away from is 7 and 15. So the moment I saw 15, I said, okay, something is wrong somewhere. I need to figure out what the problem is. Remember I said earlier that whenever I have decimal points, right, I don't like to approximate. Rather than approximating, I would say the first decimal point I'm getting to see in my row or column, right? I'm going to multiply, I'm going to divide it, use it to divide the number I want to get, right? So on this 1.4, I know I want to get 4. So what I did was I said 4 divided by 1.4, which I got 3.14 right here, right? So when I got 3.14, I began to multiply again with 3.14, right? So I started the process again. 3.14 times this guy, I got 3.14. So I approximated now and said, because I need a whole number in this row, so I said that gave me 3, right? Then 1.4 times 3.14, that gave me the 4, right? Times this, that gave me this. So now when I got here and I multiplied by 3.14, I got 16. So this is me already getting rid of 15 again. After I was able to get rid of 7, now I'm able to get rid of 15. So that moment I figured that yes, I'm supposed to be multiplying all through by 3.14. So I think this is explanatory enough. And if you did not get it, drop a comment, or you can reverse the video to listen to everything I just said earlier. So let's go back to the real question right here. Cool. So from my derivation, multiplying by 1.4 something was wrong. I got 7 in my line. Multiplying by 2, I got 7 again. Then multiplying by 3, I got 15 in my equation. Then I went ahead to multiply by 3.14. So how did I get my 3.14? What I said was I know I wanted to get 4 in the second row because my first decimal point was 1.4, which is here. 1.4, which is here. That's my first decimal point. So I said I want to derive 4 somewhere here, right? I want to derive 4. So I said 4 divided by 1.4, right? And how did I get the 4? I was multiplying by 3. So 3 times this, I was going to get 4. So I never want to always multiply decimal point with a whole number. I always want to multiply it by a decimal point so that I can get close to a whole number when I approximate. So I love to approximate things like 3.8, 3.9, 3.7, but I don't like approximating figures like 3.5, right? Sorry, this is 5. I don't like approximating numbers like 3.5. So that's why I always generate a decimal point to multiply. So that's why I got my 3.14. I said 4 divided by 1.4, which gave me 3.14. So that was why I went ahead by multiplying all of my table, right? All of these decimal points, these guys, all of everything in this place, my approximation, right? I multiplied then by 3.14. So please don't mistake this. I never multiply by pi. Some might be like, oh, I'm multiplying by pi. No, this is not pi. I generated this number myself. So it's not a pi thing. All right. Sorry. So like I said, when I began to multiply, I got 3. I got approximately 4. Sorry, I think I have to write all this number well. I got approximately 4. I got 8. I got 10. I got 12. I got 16. I got 18, and I got 19. So remember, you always want to avoid seeing 7 and 15 because it is hard to generate their HKL. So now let's begin to derive our indices. Indices, right? The question said find the let's see, yeah, the question said produce each of the peak and lattice parameter. Produce, yeah, indices of the plane. Yeah, so we are trying to look for the indices of our plane now. So from these indices of our plane, we'll be able to tell the crystal structure. So we are already solving our questions now. So for the indices of the plane, it is h, right? We are looking for h squared plus k squared plus, sorry, oh god, I'm looking for h square plus k square plus l square, right? We're going to be looking for numbers, substituting number for HKL that will give us what is inside this. I'm coming, let me change my ink to white. What will give us what is inside all of these columns, right? So let's start. For this first one, we have 3. So what 3 numbers raised to power 2 can I multiply by, can I sum up to give me 3? So when I do 1 square plus 1 square plus 1 square, which will give me 1, 1, 1 equals to 3. So this is what I said when we had to look for that of 7 and 15, we would never ever be able to derive them, right? Because you cannot use decimal, it has to always be whole number. So since I know this, my first one is 1, 1, 1, that's the indices of the plane, right? So for the next one, I have to look for what I will sum up to give me 2. So if I have 2 square plus 0 square plus 0 square, that will give me 4 plus 0 plus 0, that will give me 4. So I know my answer here is 2, 0, 0. Sorry, I think I need to reduce my ink, or is it good? Okay, let me reduce by 1. Okay, so let's go on and solve. The third one, I need to look for what to multiply to give me 8, so which is a 4 and a 4. So I have 2 square plus 2 square plus 0, which will give me 4 plus 4 plus 0, which is 8, right? So I have 2, 2, 0, right? On and on, you keep trying numbers that will generate that. So for our 10, we know it is 3. 3 raised to power 2 is 9, plus 1 raised to power 2, which is 1, right? Plus 0 raised to power 2 will give us 9 plus 1 plus 0, which is equal to 10. So that was how I arrived at my 10. So here we have 3, 1, 0 for the indices of plane. So continuously like that. For this one, I have 2 raised to power 2, which is 4. So 4 in 3 places. 4, 4, 4 will give us 12. So for this guy is 16. 4 raised to power 2 is 16. So it's just going to be 4, 0, 0. Then for this guy, 18. So I need 9 plus 9, right? So 3 raised to power 2 is 9. 3 raised to power 2 is 9. 9 plus 9 is going to give me 18. So the last one is 0. Then for this guy, I have 3 raised to power 2, which is 9. 3 raised to power 2, 19. 18. Then 1 raised to power 2, which is 1. It will give me 19. So I have 9. Sorry, I have 9 plus 9 plus 1, which is 19. 3, 3, 1. Cool. So this is the indices of the plane that we're being told to look for. So now I want you guys to pay attention to this. So this is where we get to know our crystal structure. So these are the indices of plane for each crystal structure, simple cubic, and also we are going to compare our answers here with what is here. So our first row was 111. Here the first is 110. So we know it is not BCC, right? So our first is 111. Here we have 111. Here we have 111. So for the first, we know that it is either FCC or simple cubic. Cool. So let's erase BCC from our structure. So now we check the second one, which is 200. So here we have 200, and here we also have 200. It still looks like it could be either FCC or simple cubic. So we go to the third one. We have 220. Here we have 220. Here we don't have 220. So it's already convincing that it's FCC. So let's continue checking on FCC. So the next we have 310, right? There's no 310, which is cool. Right? We check the next one, which is 222, and we have 222. We check the next one, which is 400. Sorry, I want to erase this. In which we have 400 here, right? So since we have like enough numbers that are, repeating itself in a structure, we decide that our structure is FCC. So for this place, our guy is FCC. Cool, right? So the next question is, they said we should look for our lattice parameter. So we solved to our number 1. This is our indices, right? This is our indices of plane. Then we know the structure to be FCC from this table that we just did. From this table, let me zoom in so you can get. So we had 111, we had 200, we had 220. We never had 311, but we had 222 and 400. Cool. So the next thing is to look for our lattice parameter, which is A, right? So this is the formula to find our A. So yeah, in the question we are given our lambda, which is wavelength. Remember I said most times they give us lambda in Armstrong. You have to always convert to nanometer, which is divided by 10. But here we are given our lambda directly as a normal figure. So here our lambda is, our lambda, which is wavelength, is equals to 0.15418, 0.15418. I gotta erase this so we don't get confused. 5418. Let me zoom out. Sorry, to confirm. 415,418. Cool. So our lattice parameter from this formula here, right? If we make it this other formula, we're gonna have DHKL, right? Times, dot is times, root of h square. Sorry, I gotta write that well. H square plus k square plus L square, right? So this is the formula for A, but the issue is we have another unknown, which is this guy, which is this DHKL. We don't know our interplanar spacing. This is our interplanar spacing. So we have another formula here, right here, which will help us find our interplanar space, which is n lambda. So our n here is 1, ratio of diffraction, I guess. Ratio of diffraction is 1. So we have n lambda is equals to 2d interplanar spacing HKL times sine theta. So this is why I say you always need theta and not sine 2 theta. You need theta, so that's why you need to find your theta in the table. So since our n is 1, now let's make DHKL the subject formula. So DHKL is going to be equal to n lambda, right, divided by 2 sine theta. So let's find our D interplanar spacing. So you come back to your table, you pick any one of your choice, any row of your choice. You could choose pick number 1, pick number 2, pick number 3, any one of your choice. You get to pick, but I always advise you to solve twice, right? So you can know if you're correct, right? So which one should we pick first? Let's pick that of pick number 4. So our HKL in pick number 4 is 310, and our theta is 16.6 degrees. So let's input that into this, which is equal to our n is 1, which is equal to, okay, let me just solve it down here. So for our D HKL that we are looking for, so we don't write HKL anymore. Now we have to write the indices, which is 3. We chose pick 4, right? So our HKL there is 31. You need to signify which one you chose. 310, which is equal to our n lambda, which is 1, times our lambda, which is 0.15, 15418 over 2 times our sine theta. We said our theta on that row is, on our fourth peak, remember theta not to theta is 16.6 degree. So 16.6. So let's go ahead and punch that into our calculator to find our D. Our D is equal to 0.2698 nanometer. We found our D, right? So now we are going to look for our A. A is equals to our DHKL. Still, you need to, I think we already signified our D is 310. So let's just go ahead and substitute directly. So our A is equals to our interplanar spacing, which we just got, which is 0.2698, right? Times root of our HKL. So our H is 3 square plus 1 square plus 0 square, right? This is square this. So here our A is 0.8533 nanometer. This is our A. So remember I said you should always solve twice to be sure that you're correct. So let's pick another one again. Let's do for pick 1, which our D is equal to 111, right? D is equal to 111. Let me write that way. 111. 0.111 equal to 1 times 0.15418 over 2 times sine. The theta for our peak 1 with indices of 111, right, is is 9 degrees. So sine 9, which is equal to, which will give us 0.4928 nanometer for our DHKL. So let's find our A. So if our A are the same thing, then we are very, very correct. So 0.4928 times root of 1 square plus 1 square plus 1 square. Sorry, these are all squares. Pardon my handwriting. So we say times root of 1 square plus 1 square plus 1 square, which is equal to 0.8535 nanometer. So can you see? It's the same thing. We have 0.85, 0.85 approximates to 2 after the decimal points. Yeah, so that means our answer is correct. We have the same lattice parameter, so we can go ahead and say for our first table of figure 4.7, our structure is FCC, our lattice parameter is 0.85 nanometer, and our indices of plane is 111, 200, 220, 310, 222, 400, 330, 311, 331, sorry. So guys, make sure you subscribe to the YouTube channel, share this video and like. Then let's go ahead and solve for the second one. Okay guys, welcome back. Figure 4.8 shows the result of an X-ray diffraction experiment in the form of intensity of the diffracted peak versus the 2 theta diffraction angle if X-rays with a wavelength, so we are giving wavelength 0.07107 nanometer, are used to determine A, crystal structure, indices of the plane that produces each peak, and C, the lattice parameter. So let's go ahead and solve. So remember previously I told us how to find this. So you trace this down at first. So you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 10 divided by 9. I'm going to take each distance or each point to be 1.11, right? So for this, I know I have 20, and I count 1, 2, 3, 4, 5, 6, so times, so that will be 20 open bracket 6 times 1.11. So that's how I'm going to get that. But we are lucky enough, they've given us the angles because they want to save time while they mark 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 peak indexes. So I'm going to revert all of my step now. All right guys, so in continuation, we're already given the 2 theta, that's diffraction angles. So we need to divide it all by 2. So we say 26 divided by 2, 13, 36 divided by 2, 18, so on and so forth. So the next thing we do is in our calculator, we punch sine, in our calculator we punch sine, open brackets. Our first angle is 13 raised to power 2, which will give us 0.0506, or if you never found your theta, you can go ahead and say sine is equal to 26 over 2 close bracket raised to power 2, which will give us the same 0.0506. So I had to solve this so I don't have to be punching it one by one in the calculator to save time, while I can just jump to explaining. So I did that and I got all of everything here in this row, right, or column, and so we begin to pick each of our sine squared thetas and divide them by the lowest one, in which this is our lowest one. So we divide the first one, divides by itself, we get 1, right? So you go ahead and keep dividing by orders. The next one we get one, sorry, I want to push it to the left. You get 1.89. The next one we got 2.89. The next one we got 3.30. The next one we got, sorry, 3.80. The next one we got 4 points, sorry, my handwriting, 4.73. No, 7.3. The next we got 5.55. The next we got 6.57. The next we got 7.16. Right, this is 7. So we can go ahead by okay, yeah. Okay, yeah. So this is a typical example of the reason, or this is a typical example of the reason why I told you earlier that I don't like to approximate my decimal points, and at the same time I don't like to I don't like to multiply by just 3. I love to generate my multiplication to be in decimal place. So let's go ahead and solve. I'll show you the reason why. So when we approximate this, we have, we get to have 2. When we approximate this, we get to have 3. When we approximate this, we get to have 4, which is looking simple and interesting. When we approximate this, we have 5, right? When we approximate this, we have 6. Now, when we approximate this, we have 7. Sorry, let me write it well so you can see our mistake. We have 7. Or approximately we have 7. I remember I said I don't want to have repetitive number, and at the same time I don't want to ever have 7. So in this situation, even if I multiply by 2, I'll be having 14, in which I don't want to have repetitive numbers. So can you see why I said I hate to multiply? I hate to approximate. So rather than approximating, what I always prefer to do is I love to generate something I can use to multiply. Okay, so guys, we've seen the repercussion of approximating, because by the time I approximate right here, I'll be having 7 and 7. So because I don't want that to happen, I'll just stay on my lane and begin to multiply by 2. But I already know 2 is the solution to my problem, right? Because I'll get rid of this 7 that is here. So I have to multiply through by 2. So let's begin to multiply to get our answer. So when we multiply by 2 here, I get 2. When we multiply by 2 here, I get 3 point something. But when I approximate it, I get 4, right? Then the next one, I know this is approximately 3, right? So when I multiply it and I approximate, I get 6. When I multiply 2 times 3.8 and I approximate, I'm going to get 8. Right? When I multiply here and I approximate, I'm going to get 10. When I multiply here and approximate, I'm going to get 12. When I multiply here and approximate, I'm going to get 13. When I multiply and approximate, I'm going to get 14. So can you see, I just got rid of me getting to have 14 here by not approximating, but just multiplying first, then approximating afterwards, right? So 2 times 6.57, I got 2 times 6.57. What I got was 13.14. So imagine I approximate to 7, so I'll be getting 14, which is gonna complicate things. So let's go ahead and just look for our plane indices. So remember, we are looking for what will multiply h squared plus k squared plus s squared. That will give us our answer. So if I have 1 raised to power 2 plus 1 raised to power 2 plus 0 raised to power 2, I'm going to get 2. That's 1 plus 1. So yeah, here my answer, sorry. Yeah, my answer is going to be 110,200. Yeah, I'm going to have, sorry. Yeah, I'm going to have, sorry, excuse me. Yeah, I'm going to have 211, which is 4 plus 2. Yeah, I'm going to have 220, which is 4 plus 4. Yeah, I'm going to have 310, which is 9 plus 1. Yeah, I'm going to have 222, which is 4 raised to the power 3. Yeah, I'm going to have 320. And here I'm going to have 321. So we just found our plane indices, like indices of plane. So now let's compare it to that previous table. we have 110, 200 for our first number. So we check here, we know we have 110 here, we have 110 here, we have 200 here, sorry, we have 200 here, and we have 200 here. So it's either BCC or simple cubic. So let's check again the next figures. Sorry, where is our table? So 211, 220. So we come back, there is 211 here, there is 211 here, but we don't have 220 here, we have 220 here. So another number that can exist that will help us is 310, 222. So let's check, do we have 310, 222? So yeah, we have 310 and 222. So guys, we can go ahead and just say, sorry, excuse me, we can go ahead and declare that this is a BCC structure. So now let's look for our interplanar spacing and our what's it called? Interplanar spacing and our lattice parameter. So for our interplanar spacing, we know it is DHKL is equal to n lambda over 2 sine theta, right? In which we are given our lambda in this question. I think it was 0.07 something. Let's confirm. Yeah, it is 0.0707107, right? For our lambda, excuse me, this is our lambda, right? This is this guy, our lambda, right? So let's begin to solve. It's going to be equal to 1 times 0.07107 over 2 times, oh, we've not picked our DHKL, so which one should we use? Peak. Let's use peak 2 this time around. So our peak 2, which is this guy, our DHKL there is 200, right? 200. So here we have sine, our sine theta here is 18, our theta there is 18. So let's input that into our calculator and see what we get. 0.07107 over 2 times sine of 18, which will give us equal to 0.1145. Sorry, this is 5 nm, right? So let's find our A, lattice parameter, right, which is DHKL times our root of h square plus k square plus l square, which is equal to our DHKL is 0.1145, sorry, 45 times root of, we chose 200, so yeah, 200, 2 square plus 0 square plus 0 square. So let's punch that into the calculator, times root of 2 square plus 0 square plus 0 square, which is equal to, so our lattice parameter is going to be equal to 0.22997 nanometer. So I intentionally wrote this long figure because if we approximate, it's going to be so different quickly. So guys, I'm going to stop here. I need you to solve using another peak for the DHKL, then find your lattice parameter and compare them. Please and please drop a comment at the comment section saying yes, the lattice parameter is the same. Please, let's do that, guys. I really wish to see that in the comment section. Make sure you drop a comment there confirming that yes, our lattice parameter is the same thing. I want to take that risk of not confirming but entrusting it in your hands. So guys, Midekali here. Thank you for watching our video and subscribe to the YouTube channel. Make sure you share to your colleagues. Bye and peace out.